Hi, my name is Andrew Nazareth, and this is Lab 5, Faraday's Law for Physics 2212. In this lab, we want to visualize Faraday's Law by determining the amount of time it would take for a magnet to fall through a tube of aluminum foil. We are also going to create a computational model of this experiment through GlowScript. There are four key concepts we will use when conducting this experiment. First, we have Faraday's law, where the induced voltage in a circuit is proportional to the rate of the change over time to the magnetic flux in that circuit. We also can use the Biot-Savart law, where the magnetic field at any point is directly proportional to the current in a wire and inversely proportional to the distance from the point to the wire. We also have Lenz's law, where the magnetic field generated from induced current flowing in a loop is always opposite in the direction of the change in flux through a loop. And finally, we'll be implementing Newton's second and third laws. Some of the equations we'll be using are on the right-hand side of the slide. Here's the procedure for this experiment. First, you find the north end of the magnetic dipole. Second, with one hand, hold the tube vertically and place the magnet just over the top opening. Third, you record the magnet entering and stop recording when the magnet leaves the tube. Four, just find the time of the video that the magnet takes to fall through the tube. Then you want to repeat this experiment 5 times and calculate the average time that the magnet falls through the tube. Here are the measurements I took when conducting this experiment. The aluminum tube has 0.3 meters length, a 0.006 meter width, an inner radius of 0.025, a radius of 0.032 meters, and I calculate the magnetic dipole moment from the third lab, which is 4.96 newton meters times over 1 Tesla, and the magnet's mass is 0.024 kilograms. Also on the right-hand side, we have each of the trials from the experiment, and I received an average time of 1.25 seconds. All right, now let's move on to the GlowScript code, where I first define all the dimensions of the tube and also recorded the magnetic dipole moment of the magnet and along with its mass. I then created two new methods. The first one, which calculates the magnetic field of a dipole at any location, and the next, which calculates the derivative of the magnetic flux based on the magnet and for each ring. I then found the current for each ring by taking the derivative of its magnetic flux and dividing it over the resistance of each ring. And next, I then calculated the magnetic force on each ring by taking the circumference of the ring and multiplying that by the current and magnetic field by the angle. Finally, I found the total net force of the system by finding the gravitational force of the magnet and adding that up with the magnetic force it generated. All right, now here's a GlowScript simulation of this experiment where the red ring represents the north end of the magnet and the blue ring represents the south end of the magnet. The red ring and the blue ring fall from top to down. Now here is a graph comparing the instantaneous velocity of the magnet falling through the tube versus the time it took. And this was all based on the mu value of 4.96 amperes times meter squared. The time it took to fall through the tube was at a total of 1.15 seconds, which was a lot less than the average time I found through running my experiments, meaning either the mu value was calculated incorrectly or one of the measurements I made was incorrect. Now let's take a look at things if they're run a little bit differently in this experiment. For example, what if the resistivity of the conductor were reduced as close as possible to zero? And how would the dynamics of the experiment change as the falling magnet changes? Well, first off, when you think about it, induced current would increase, which as a result would increase the time it would take for the magnet to fall through the tube. All right, let's also consider if there were holes cut into the tube, how would that affect the rings in our model? So in our model, it would not have as many rings, which as a result would reduce the current and the magnetic force. Magnets would also fall through the tube in less time, making the experiment go a lot faster. The big takeaway of this lab was that it helped us understand the applications of Faraday's law. Now, even though there was an error in the lab, we weren't able to match our real-life findings with our computational model. But overall, this lab helped us gain a better understanding of magnetic flux and induced current. And yeah, thank you for watching this video.